All right, guys, welcome to part 2 of our notes over power and efficiency. And so real quick, let's talk about something is efficient. So an electric heater plugged into the wall, it is about 95% efficient. In other words, 95% of the power you get from the wall is turned into heat, and that's kind of what it's designed to do. A car is about 30% efficient. And then while that's not great, if you think about the actual moving of a car that weighs that much, that has that many moving parts, that's actually really good. The majority of that energy loss is due to heat, the heat generated inside the motor and etc. An old school light bulb, an old school incandescent light bulb, is about 3% efficient. It is designed to produce light, but a lot of the energy goes to heat, right? So this is, once again, this is not an LED bulb, it's a old school incandescent, so it's a little different. So we have a couple different ways to define efficiency. So we usually say like efficiency is, it's the work out divided by the work in, so the work output of the system versus how much you had to plug in, you multiply that by 100 to get the percentage. The other way to think about it is the power into the system versus the power out of the system times 100. And so you're not going to get anything that's over 100% efficient. If you did, you probably put something in the wrong spot. All right, so let's take a look at the first example here. We have an object that was raised a certain distance. So we're going to calculate in part A the theoretical amount of energy required to do this. Well, work is force times distance, and it looks like it's the change in energy. So if I look at it this way, if the original height is 0 and the final height is whatever, so it's really just the potential energy difference here. So it looks like this 2,800 times 9.8 times 120 meters. So we get about 3.29 times 10 to the 6th joules worth of energy required to do that job, okay? Well, in reality, we had to accelerate this object. It was accelerated from rest to a speed, and so that 193 kilometers per hour converts to about 53.6 meters per second. If we use the same principle, work is the change in energy. We know there's a change in kinetic energy. The original velocity is 0, the final velocity is 53.6. So we can just use this guy here. So this is 1/2 the mass of 2,800. Velocity is 53.6 squared. So we get an actual work output of 4.02 times 10 to the 6 joules. We then want to calculate the efficiency here. So for part C, the efficiency looks like it is the work output divided by the work into the system. So the work out, so that's the theoretical piece up there. That's that 3.29 times 10 to the 6th. Over what actually had to happen to make the thing move, all in joules. You get about 82% efficient. So the motor or whatever was used to move it up that high was about 82% efficient, which isn't too bad. All right, so we have another example here. So we have a roller coaster, and the idea about this roller coaster is it starts up at the top, goes down, and then whatever happens, there could be loops and everything, but then it ends somewhere over here. So it starts over here, has some kind of high point, does something, and then ends over there. And in the process, we're going to assume there's going to be some kind of energy loss due to friction, and that's kind of what the last part of the question asks us here. So the first thing we ask is find the power output from the ride, okay? So the original piece, so we're going to find the work out, and it's going to be the change in kinetic energy plus the change in potential energy going up that hill. So the original change in kinetic energy is just the 1/2 mv squared. So if I plug all of this in here, 4,500 and 17.8. So 17.8 is the 64 kilometers per hour converted. Sorry, I did that and forgot to tell you. And so the original kinetic energy here is 7.1 times 10 to the 5th joules. There is a change in potential energy. This is just mgh. So this is the mass times gravity times height, 34 meters. And so we get about 1.5 times 10 to the 6th. So we get a total energy here. This isn't kind of part of the equation, but I might need this later, hint, hint, nudge. The total energy required to move that thing up there was 2.2 times 10 to the 6th joules. That total energy there is what we're going to use to calculate the power. So power is the total work out divided by the time. So this total energy here is the total work out, right? So remember, work and energy, they're synonymous. They're the same thing. So we get 2.2 times 10 to the 6th joules over a time interval of 2 seconds. And so we get about 1.1 times 10 to the 6th watts, or 1.1 megawatt if we're converting that way. So that's how we calculate the power done. Part B, if the total power consumption was actually 1.45 megawatts, so for part B here, we want to calculate the efficiency. So we're going to go power out divided by power in. Well, what was actually put out of the system was that 1.1 times 10 to the 6th joules of energy. And the actual power plugged into the system was that 1.45 megawatts, or 1.45 times 10 to the 6th joules, watts worth of energy. This is a watts there, my bad. So we get about a 76% efficiency from the roller coaster. All right, so part C adds the heat question, okay? And so if we consider conservation of energy, we know that there can't be any losses, okay? Over here, kind of going back and forth here, that's that 2.2 number. Going to a new page here, for part C, we know that the total energy must be 0. In other words, I have to account for everything. So the initial energy in the system is the kinetic energy in the system plus the energy at the heat. So this is how fast he's coming at the end, basically. This initial energy here is that total energy. So when we plug stuff in, we get something that looks kind of like this. So that total energy is 2.2 times 10 to the 6th. The kinetic energy here is the 1/2 mv squared, so it's this 8. That's how fast he's coming into the thing there. Then I have this energy loss due to heat, so I have to add it there in order for because what's happening here is he's not going as fast as he should be. If we just do straight conservation of energy, right? If at the top of the hill, position 1, position 2, all of the potential energy at the top has to equal all of the kinetic energy at the bottom, right? But that didn't happen here. What happened is on the way down, energy was lost due to friction, and that should make sense, okay? So when we do the math, we get the energy sub H, E sub H, energy loss due to heat, is about 2.21 times 10 to the 6 joules lost to heat. All right, so after this, part D asks, what was the net force, what was the force required to bring the car to a stop? So that's pretty straightforward. We can say work is the change in energy. Work is also the net force times distance. And so what we're going to do is we're going to use this chunk here to solve for the net force. Let's set it up this way. The net force required to stop all of this is equal to the final kinetic energy minus the initial kinetic energy over d. So we changed the delta E into the delta KE. What happens here is there's no final velocity, right? So there's no kinetic energy. So the equation turns into this. The net force is negative KE initial over distance, which is negative 1/2 m initial velocity squared over d. And I have all of that information. So here we're just crunching some numbers here. This 8.0, that's how fast it comes into the station. It stopped over a distance of 2 meters. So the net force stopping this guy, right, he accelerated it in the negative direction. So I get a net force of negative 7.2 times 10 to the 4th newtons. That is the net force to stop the object there. All right, so there's a lot of information there. One thing to kind of be cognizant of is the power is work over time. So this is a pretty simple equation in and of itself. But we have several different ways to express work. Work is force times distance. Work is the change in energy, and that could be potential energy, there could be kinetic energy. Sometimes there's energy loss due to heat, and we have to figure out where that goes. Do I add it? Do I subtract it on certain pieces? So there's lots of different things we can do to set that up. Understanding all of this is going to be important here. The net force idea, that is going to be with us for a long time. So understanding what forces are acting on it. Does it accelerate? Does it move at constant velocity? Is it positive? Is it negative? Why is it positive or negative? So just be sure you have a handle on those as we progress through these things. So if you have any questions, let me know. Thanks for watching. Bye.